So we need to know the area formulas for those shapes. Okay. So for example, okay, the formulas that we need to know.
Do we need to memorize these?
Well, yeah, I would say, but hopefully you know some of them already. All right. So for example, what's the area of a square?
S.
Yeah, so side squared is the key one we remember there. It's A equals side squared. Okay? That's the area of a square. Okay. What about the area of a rectangle? Yeah. Length times width, but we're going to use it, we're going to write it in a different way. We're going to say it's going to be a side times a height. Side times a height. And you might wonder why we write it in that kind of way. Why not to say length times width? Well, it'll make more sense. We're writing all of these formulas in terms of a single side. Of course, rectangle you need the height as well, but you'll see how that kind of plays out here. What about the area of a semicircle? Yeah. So we know the area formula for a semicircle is area equals 1/2 pi times, and I'm going to write this in a weird way, side over 2 quantity squared. All right, and I'll explain why that is the way it is in a second here. It'll make more sense. And in fact, if you don't want to memorize this, it might be more beneficial to memorize it in its more traditional sense, pi over 8. Or it's like simplified or reworked form there. Pi over 8 times side squared. The way we get that is that if you have a over 2 squared, that becomes over 4, and the 1 over 4 times the 1 over 2 becomes then the pi, well, pi times 1 over 2 times 1 over 4 becomes pi over 8. And so it's just pi over 8 times side squared. Okay? And again, this will make more sense hopefully in a few minutes, but just right now let's have that written. And then the last one, and this is the area of an equilateral triangle. And this is the one that appears the least often, but I do believe it appeared last year. Do you remember, Mackenzie? Was there equilateral triangles cross-section problem on the test last year? Okay, you don't. Okay, because I think it was like within the last year is the year before I think where it popped up. So. I know. It was like almost a year since you've done it. I just don't remember. Yeah. Okay. That's fine. And this formula is going to be side squared times root 3 over 4. Okay? And it works out that way. Again, we know the area formula for a triangle is 1/2 base times height. But since we're talking about specifically an equilateral triangle, we can actually rework it in just terms of side squared times root 3 over 4 if we kind of manipulate things around there. Okay? But there are your kind of four possible cross sections we need to be responsible for. All right. So I've thrown all this information at you, but we actually haven't seen one of these yet. So let me show you what kind of is we're going to do here, how we're going to do this. So let me start with an example. And we're going to find the volume, okay, of a solid whose base is the region bounded by the lines f of x equals 1 minus x over 2, g of x equals negative 1 plus x over 2, and x equals 0. Okay. The cross sections perpendicular to the x-axis are, and let's start out with squares, just to kind of make life easier for ourselves to start out here. Sorry, I'll scoot that up. I'll give you guys a chance to catch up on that, and I did that on purpose. So a basic sketch of how this region looks. Okay, we have, so for example, f of x here, this is actually a line, right? F of x is a line. It's got a y-intercept of 1, and it's got a slope of -1/2, right? It's x over 2, but that's the same thing as -1/2 x. So we're going to go down 1 and right 1, 2, and so there's where our line goes, and so it's going to kind of go from there to there. And then this is also a linear equation with y-intercept of -1 and slope of +1/2, so up 1, right 2. Okay? And then x equals 0, which is the y-axis here. And so this is our region right here. Okay. And so we've seen regions like this before. Right? And so we could find the area of this region, for example. If we want to do the area of this region, if we wanted to find the area of that region, what would we do? The integral from what to what? From 0 to 2. Okay, so if we just wanted to find the area of this region, so we're not talking about volume right now. If we just want to find the area of this region, we do the integral from 0 to 2 of what? Yeah, right.
Negative.
No, not the answer. What would the setup be?
Oh, integral from 0 to 2 of g of x minus f of x.
We want to do top curve minus bottom curve. So it'll be f of x minus g of x.
Yeah, isn't g of x something?
The 1 minus x over 2, y intercept is positive. So it'd be, yeah, so the integral for this region would be the integral from 0 to 2 of f minus g, and that would give you the area of the region. But that's not what we're interested in here, right? We're interested in a solid that we're creating from this. And this region is the base of our solid. It's the bottom. And so if you will give me just a moment here, I'm going to show you kind of what I mean by that. So bear with me here as I switch technologies. Try to show you things.
It's really a 2 forwards.
Okay, so here, if you look, can you see this okay?
Mm-hmm.
Yes, no, let me see if I can, like, if I zoom in, I wonder if this will help. Nope, the applet will just literally go back. Okay, so I want to, yeah. So anyway, so here's our region, right? You can see there's you know, our bottom curve, 1 minus x over 2. Actually, these are supposed to be swapped, sorry. I don't know why these are written that way, but they're backwards. This top, yeah, the functions are backwards. They should be upside down, or, you know, this one should be up here, this one should be down here. But anyway, you can still see the region that we just had, right? That was what I just drew on the paper right there, okay? And so, to create our solid, if you look over here to the right now, you'll notice that we've kind of changed our orientation. You'll still see like the light blue region there, and now since we're talking three-dimensionally, it's kind of like skewed, but that's this light blue region is the same as this light blue region right here. Okay, and the way we're going to build our shape, again, we're using squares, so I'm going to click this one. And so you can see right here that the square is coming up off of our region there, going over and coming back down, and that creates a square. And so you can kind of see how the solid's going to get built. As we move further out towards the 2, the squares get smaller. Why do the squares get smaller? Because the distance between the 2 curves there is closer, and so that requires that the square, that's our cross section, has to get smaller. As we move backwards, the square gets larger because the distance between these 2 curves, okay, is increasing, and so we have larger squares. All right, and so you're but Mr. Okay, so does that make sense so far? We have all these different size squares. All right, so it's like, but still, where is this solid? Well, it occurs by stacking up all these squares. So starting from this square right here and continually adding on square after square after square, stacking it up, all these cross sections, we accumulate them and we create this solid. Okay, so hold on a second. So there's the solid that gets formed from that setup. Anna, question? Never mind. Okay, so there's the solid.
Looks very satisfying.
Okay. You can kind of see it right there. There's again our base. All right, and you can see those squares like stacking up. Ugh, now it's getting all. Okay, sorry.
I have a question.
So there's our shape. I can hide the edges so you can see like the smooth and hide the cross section there. So there's our smooth shape.
I have a question.
Yes, question.
So, the way your graph is oriented right now, your y-axis is going close to far.
Yeah, so
Why is it
this
oriented like that?
this is the y-axis
Yeah.
right there, and then that's the x-axis right there. Just to show you how the solid's being created.
Okay.
So right now, when we look at it this way, this is like a top-down view of our solid.
Mhm.
Right? We're looking from the top down onto it, so we see the base, and the squares pop up, off, down, and go back down to the curve. So the squares all stack on top of that base.
And then do they stack below as well?
No, our squares we're going to say are on top, above. They stack on it there,
Why don't they stack below?
because we're told that the region is the base of the shape.
Okay.
If they were below, that wouldn't be the base of the shape anymore.
Sure.
So yes, Brandon, and then Connor.
This kind of like problem would never be like they give you a volume, I guess, and then say what shape to get this. It would be more of they tell you what shape it is.
They give you the region, they'll give you the cross sections, yes. Yep, exactly right. So, how do we actually find the volume of this? How do we find the volume of this? Well, we go back to, and I have to switch over back now to my problem here. Okay, we go back to our formula here. The formula for the volume of a solid of known cross sections is merely the integral of the area of those cross sections. So our integral is going to be volume equals the integral from a to b of a of x dx. Okay? Since we're integrating with respect to x here, everyone here should know what are our limits of integration going to be, from what to what? 0 to 2, that's right. So we're integrating from 0 to 2. Okay? Now, since we're using squares, the area formula for squares is side squared. Okay? What measurement here is determining the length of the side of those squares? Is it just f of x, the distance from here up to f of x? Is it that distance? Is this the side of our square right here?
Oh, no.
Not from the axis up to f, no, and it's not from the axis down to g either. So it's not f or g alone, it's f's height minus g's height. It's the full length there. So it's going to be f minus g. That'll give us that full length. So it's the side is f of x minus g of x quantity squared dx. Side length, right? The side length here is from here down to here. That side length is top curve minus bottom curve, right? Sorry. The side length here is from top curve down to the bottom curve. And so we subtract our functions and square, right? Side squared dx. Side squared dx there. Okay. Which is, in our terms, since we know what f and g are, f is going to be 1 minus x over 2 minus negative 1 plus x over 2 quantity squared dx. So there's f and there's g. Okay. So there's our setup.
Sure.
Yes. Sorry, Connor, I never came back to you.
It doesn't matter which one is first, so we're just going to square it.
I guess so, that's true. It wouldn't matter if you do g minus f or f minus g, yeah. But you obviously do need to do subtraction, but in this case, since we're squaring, yeah. And I guess that it will only matter for the area of a rectangle when we get to that one. So, yeah, Brandon.
So, I guess if entire triangle was moved up,
Mm-hmm.
it would no longer become x minus gx.
I think it still would work, yes. Because it'd be top curve minus bottom curve. It would still yield the right distance.
So it works no matter where
The orientation, I think, yeah.
it could
Mm-hmm.
be 10,000 spaces away from the x-axis.
Mm-hmm. Because the f of x will be 10,000 plus that much higher than the g of x, and then you just subtract f and g. They'll both be shifting up 10,000, so they both, when you subtract them, the 10,000s will cancel, and it'll still be f minus g. So that's the idea, yeah. Good question, yeah. Okay. So there it is. And as a result, then we can find that volume, okay, so we have to be careful, Math 9, integral from 0 to 2, we've got to be out of here, 1 minus 0.5x minus negative 1 minus 0.5x, and then that quantity squared with respect to x, and you should get 8. Okay, so it's 8.
Oh my goodness.
How crazy is that? Solid with a volume of 8. Okay. Let's try another one with a different cross section now. Okay. So any questions on that? It's a lot. I understand. It's not easy. It's like funky. It's hard to visualize because it's 3 dimensions and it's at a different 3 dimensions than what we did before. Okay. So okay, let's try just for fun. Let's try let's use a semicircle. Okay, so let's try this using semicircles. So, what kind of solid will we be creating if we use semicircles as our cross section here?
It'll be like a cylinder kind of looking. No, it'll be like a cone.
Okay, so I hear predictions about being like half of a cone. Can you guys see that? If we had a semicircle kind of come up, around and back down, come up, around and back down, come up, around and back down, it would create half of a cone. Well, let's see if that prediction is correct. I can actually change the cross sections here of this shape. So let me ungenerate the solid here, and we'll go to semicircles. Okay, so you can see the semicircle there, right? So as we move that semicircle further back, it gets bigger. As we move it in closer to the 2, it gets smaller. And so if we generate the solid, sure enough, we create half of a cone. Half of a cone. Okay? Because of the shape of the object, for the shape of our region here. Creates half a cone. Okay? But let's actually find the volume using calculus, because we could find this using just geometry formulas, right? Okay, let's do it using calculus, though. So we'll go back and set up our volume here. Okay, so again, volume is going to be the integral from A to B of the area of our cross sections times dx there. Okay. What are our limits of integration going to be here? 0 to 2 still. We're still integrating with respect to x, so it's 0 to 2 is the region. Okay, the area for a semicircle, we said was pi over 8 times side squared. So pi over 8 times the side. Well, what's determining the side length here? F of x minus g of x. It's the same thing. Okay, and that's why we kind of try and orient all of these formulas to be in terms of side, because once you know that side, then you can just basically switch it up real quick. You just, instead of, here it's side squared, so it's f of x minus g of x squared. Here it's going to be f of x minus g of x times height. We'll get to a rectangle one in a little bit here. Here, if we want to do equilateral triangle, it'd be just f of x minus g of x quantity squared times root 3 over 4, and then here for the semicircle, it's pi over 8 times f of x minus g of x quantity squared. Okay? So there it is. So, what can I do with this pi over 8?
Did you have to square that?
Yeah, sorry, I forgot the square. What can I do with this pi over 8? It's coefficient, so where can it go? Out front. Now, do I need to type this integral in my calculator? What's the answer?
Pi.
It's pi, right? This integral is what value? 8. We just found it. It's 8. So it's going to be pi over 8 times 8. which is just pi. Now, granted, in other situations, you might have to redo it, kind of thing. But in this case, it kind of worked out nicely, and so it's just pi is the answer. Okay. Now let's think about here. The volume for a cone is 1/3 times pi r squared times h. Okay. The radius of the bottom of this cone is 1, so it'll be 1/3 times pi times 1. Oh, you can't see it. Sorry. 1/3 times pi r squared times h. The height is 2.
We need to multiply it by half, right? 'Cause it's,
We need to multiply it by 1/2. And so, let's see here. It should be height of 2, 1/2. So we get 1/6 times 2 pi. So we get pi over 3.
You what?
You what, mate?
Classic Facebook.
Something is amiss here. Let's see. This should have worked because it is, radius is 1. Pi r squared h. Radius squared is 1. Height is 2. Something's not right here. Question. You didn't get 8? What did you get? Okay, let me see.
Yeah.
Oh, you know what? I see I made a mistake in my integral in my calculator here. It's not 8. It is 2.66666 something.
Yeah, okay.
Thank you. So it's 8/3 is the answer there. Sorry about that. And so it's then pi over 8 times 8/3, and so it becomes pi over 3. Aha.
I knew something was amiss.
Sorry. Thank you, guys. Yes. 8/3 was the answer, pi over 3, and so now they do match up. Thank you, James, for saying something.
I hate that page.
Okay.
Stupid.
Okay, sorry about that, folks, but there it is, fixed. Okay, let's try another one here with a different region. Unfortunately, I don't have another applet that can show us this solid, okay, so we'll have to kind of just use our imagination, okay? So, let's try another one here.
Another one.
Okay, let's find the volume of the solid. Actually, I do have another one. Whose base is the circle. X squared plus y squared equals 4. And where cross-sections, I'll keep an eye on things, Ryan.
Thank you.
You're welcome. Where the cross-sections areas are all, and we'll start with and we'll start with square. We'll do squares again. So we'll find the volume of the solid whose base is the circle x squared plus y squared equals 4, and where cross sections areas are all, in this first case, squares. Okay. So again, let's sketch a graph of our region here. Okay, this circle is centered at what point?
Origin.
Okay with that? It's the origin, 0, 0. Okay, right?
False.
What's the radius of this circle? That's true, that is right. What's the radius of the circle? 2, right? This is r squared, so we're going to count 1, 2 away, 1, 2 away, 1, 2 away, 1, 2 away. So we create our circle here. Ugly though it may be. Something like that. So again, we have to imagine here, this is the base of our region. The cross sections are going to be, and I think we want them to be perpendicular to the x-axis. I'll write that here. Squares perpendicular to the x-axis. Okay, so they're going to be perpendicular. So the slices are going to go this way, and they're going to come up, over, and down. Right. So you're going to come up, over, and down. Right. So here, will the square be bigger, or is the square bigger or smaller than at 0, for example? Square here. It'll be smaller, right? Because the space between these two is smaller, so that requires that we'll have a shorter square, right, than the square right here that's going to come up, back, and down, okay, like that. So, I do actually have an applet for this one here. Let's see if I can show you right quick. I do. Here we go. So let me show you. So there's our circle when it pops up. There's our circle, right? Radius of 2, center at the origin. Here are squares. So you can see as we move further to the left, notice that our red region here is also moving to the left as I move the little slider. The squares do get smaller the further left you go. But then as we move in closer to the center, there's the biggest square we get, and it gets down smaller. And so the region that we're going to create looks like this. Or the volume we create looks like that.
It's a weird looking region.
Okay, I don't even know what that looks like a knob or something maybe that you'd like twist. I don't know. It's weird. But there it is. Okay. So that's our solid. Okay, you can see it now. Again, you got to kind of translate from here to here. The squares come off and stack up on it. Okay. So let's go back to our setup here. Volume equals the integral from a to b of a of x dx, right? Same thing. Okay. What are our limits of integration going to be here? Let's go to Brandon. What do you say, Brandon?
They should be -2 to 2.
Good. Yep. -2 to 2. Those are x limits of integration. The furthest left we go is -2. The furthest right we go is 2. Okay. What's determining the side length? You can draw in a little like representative rectangle here if you want to. What's going to determine the side length of our square here? Let's go to... Actually, I'll take volunteers for this one. What do you want to say? Because this one might be kind of tricky to figure out.
Side length?
What determines the side length here? Ryan?
Just the integral of... Wait, oh, is it... Okay, so... Is it the integral from yx or y squared minus x squared?
Kind of on the right track. I think I see what you're trying to do, but
Do we
awesome.
have to solve the equation of the circle?
Right, so we need equation of the circle. Right now, this is not very helpful, right? This curve, okay, while it does make a circle, we need to rewrite it, and so we got to solve it for, what should we solve for?
Y.
Y, right? Because we need this to be all in terms of x, so we need to get this equation in terms of x too.
Matter, but, I mean, I guess it's Y.
Okay, well, yeah. So y squared equals 4 minus x squared. Not supposed to be equals to a minus there. And we square root both sides, right?
Where's your 4?
4 stays there. Subtract the x squared over.
4.
It's 4.
I thought that was a y.
4. Okay, my handwriting is sloppy, but there it is. So we get y equals plus or minus the square root of 4 minus x squared, and we can kind of see where this plus or minus part comes from. The plus square root of 4 minus x squared is this top arc. The minus square root of 4 minus x squared is the bottom arc. Okay, there's the negative square root of 4 minus x squared.
So could you just take the area of the top one and then multiply by 2?
You could, yes, you could. But I'm going to suggest we do, so the distance here is top curve minus bottom curve. So it's side squared, so top curve is square root of 4 minus x squared, minus the bottom curve, negative square root of 4 minus x squared, quantity squared dx. Okay? Top curve minus the bottom curve there. Which, when we simplify that, is really just the integral from negative 2 to 2 of 2 times the square root of 4 minus x squared squared.
And that's where you get to 2.
Right? Minus negative becomes plus positive, and so it becomes 2, and then when you square it, it becomes
I like it.
4 times the quantity 4 minus x squared. But we can, again, just do this in our calculators at this point if we want. Okay, so math 9. Integral from negative 2 to 2 of 2 times the square root of 4 minus x squared. Ooh, I don't need that. Squared x. So again, don't forget here, guys, it's side squared. Every one of these area formulas has a side squared in it except for rectangle, because rectangle does side times height. But there's the setup. Hit enter. And 42.666666, which as a fraction is 128/3. Okay.
I didn't get.
Questions on that one? You didn't get that?
I think I goofed somewhere.
Okay.
Yeah, because when you square the 2, you get 4. That's funny.
Okay. Yes. When you square the 2, you get 4. Exactly right. Okay. Let's try different. What other cross section you guys want to try?
Equilateral triangle.
Equilateral triangle? Rectangle? Triangles? Or let's try the equilateral triangle. Okay, equilateral triangle. We haven't done that yet. Okay. So again, I'll show you the solid here first. So we're going to do equilateral triangles. I'll just show it to you here real quick. So you're going to get the same region, our circle. And now we'll do equilateral triangles, which are right here. Oops, I kind of gave it away there. Okay, so you can kind of see, again, as we move here, the triangle gets bigger because the space between the two curves is wider, so it has to make a bigger triangle. But then as we move closer, as the curves get closer together, the triangle has to get smaller. And so then as we generate the solid, right, just kind of like wedge shape. Okay? It's kind of wedge shape.
It looks like Patrick's rock.
No. Patrick's rock looks just like a rock.
What the what? Why did it go to equilateral triangles? I said it. Equilateral triangles. It's not doing it. Weird. I know, right? There we go. Okay, so there's the solid. Okay? Hide the edges, you see it smooth. Okay? So anyway.
Ryan, you really
Hello, yes, I'm Ronnie Pelez.
You got the money?
Okay. Where's my money? All right. Anyway, equilateral triangle. So volume equals integral from A to B of the area function. Okay. Do our limits of integration change?
No, boy.
Nope, they're still the same. So it's negative 2 to 2. What's the area formula for equilateral triangles?
Side squared.
Go back to your notes.
Square root of 3 over 4.
Yeah, it's side squared times root 3 over 4. So it's side squared times root 3 over 4. But where can this root 3 over 4 go? Out front. Shh. It's a coefficient. Focus up here, guys. This is calculus. More important. Okay. Side squared. But we already know what this integral is. What's this integral? It's what we just did, 128 over 3. Okay, now granted, I will tell you this right now. On the AP test, you're not going to be asked to do it with one set of cross-sections and then switch it up to a different set of cross-sections. More than likely, you'll just be given one problem where you're asked to then just do the base with the cross-sections.
Well, it could be like a free response. That's what you're saying?
Yeah, we'll see. Yep, actually, there's the practice I gave you today has that in there. So it'll be just root 3 over 4 then times 128 over 3. Okay, which yields 128 square root of 3 over 12.
Which is 18.8.
Which is 32 pi over 3. Sorry, 32 root 3 over 3. Okay, or as a decimal, 18.475. Approximately. Okay?
Ta-da.
All right, there's one more I want to show you, and then I'll have you guys try one on your own here. And we haven't talked about rectangles yet. We've seen everything else but rectangles. So here's the trick. Rectangles is the only area formula that we're given that has not side squared, but it's side times height. And so the reason why we have this extra dimension thrown in, so for example, we do squares because it's easy, it's just one dimension squared. For the semicircle, it's again just one dimension, side being squared, then times pi over 8. Same for the equilateral triangle, it's one dimension. We can write the formula in terms of one dimension squared times root 3 over 4. But here we have two dimensions, separate, side and height. The key is at the height, though, you'll always be given a relationship to figure out what the height is. So in this particular problem, let's do a rectangle whose height is 3 times the side length. And again, we'll say it's perpendicular to the x-axis. Just so we can keep it all in terms of x here. Okay. So we'll go back to our volume formula. Volume equals the integral from A to B. Notice again, no pi's out front, right? We're not revolving here, so there's no pi's to put out front. So it's we got to be very careful when we're finding volumes. If we're finding the volume of a solid of revolution, pi goes out front. If we're finding the volume of a solid that's not revolution, it's like a cross section. We may have a coefficient that we can pull out, but we don't put a pi out there just because it's got to be in our area formula to start with. Okay, so what are the limits of integration going to be? Still the same region here we're talking about. So yeah, still negative 2 to 2, right? Still talking about this circle. So we're going to integrate from left to right, negative 2 to 2. Area for a rectangle is side times height. What's the side length of our circle? Or what's the side length of a cross section that comes up off our circle here? It'll still be top curve, minus the bottom curve here. It's top minus bottom for that full distance there. Okay, so it's top minus bottom. We already did that earlier, so I'm just going to go ahead and utilize that. It's top curve minus the bottom curve, so it just simplifies to that. So I'll just go ahead and call it that. So this equals the integral from negative 2 to 2 of, 2 square root of 4 minus x squared. Okay, but notice I'm not going to square it here because it's not side squared, it's just side times the height. Now we have to multiply this side here then by the height. But what's the height?
3 times that.
The height, that is 3 times the side length. What's the side length? 2 root 4 minus x squared. So 3 times that will be 6 square root of 4 minus x squared dx. Like so. Okay, it's just 3 times the side length there. That's it. Okay? And so we can simplify this sum, right? 2 times 6 makes 12. What's root 4 minus x squared times root 4 minus x squared? Yeah, it's 4 minus x squared.
just take 6 out and coefficient and then just use the value you had before. So it would be like 6
That's
times
exactly what happened. No.
2 root.
We could do that, yes. We could do that, yes. Well, ooh,
won't
be careful.
have that
We wouldn't want to take the 6 out. We would need to take out 2. We need to make this a 4, not a.
Yeah.
But you could do that though, still with a little crafty manipulation. Absolutely. Okay, and so then that would yield 12 math 9 negative 2 to 2 4 minus x squared 128. Okay. Of course, you don't need to simplify these at all. You can type this into your calculator at this point and then get your answer. You don't need to simplify it. So you could literally just get to this point, say equals, and then 128 there too. That's fine as well.
I did it like way before. I just put like the lines and the y equals.
Oh, Christian got a bow tie on too. I didn't even notice it. It's disguised.
Yeah.
It was in disguise.
And
Nice. Suddenly bow tie. Okay. So there it is. Very nice. All right. So let's see if I got a spare one here for you guys to try. We have a few more minutes.
Spare bow tie?
Spare bow tie. Okay, I do kind of have something here for us. All right, so let's say let R be the region bounded by the graphs of y equals the square root of x and y equals x over 2.
We denote those as f of x and g of x if you wanted to.
Say again?
We denote those as f of x and g of x.
If you wanted to, sure. Okay. Okay, and we'll put an A here. So the region R, we're going to do more parts, but not today because we're running out of time. The region R is the base of a solid. Whose cross sections are squares perpendicular to the x-axis. Okay, find the volume of this solid. Okay. So you have a little bit of extra footwork here because I don't give you a graph or anything like that. However, you have your graphing calculators, so I feel like it's, okay for you guys to kind of just get that graph there. Okay, so use your you can use your graphing calculator to help you get the region there if you want. Although really this one you don't need a graphing calculator for. In fact, this one is a non-calculator problem. So if you want to try without a calculator, it might not be a bad idea. Just give yourself the extra challenge there. Okay, I'd recommend you kind of, actually I will go ahead and give you the graph and they give it to you in the problem here. So I'll draw it out here. Okay, because you're given it in the problem. So
This is not a graphing calculator problem?
this is non-graphing calculator problem. Okay, so let's see here. We have the line that goes here from 0, and this is all 1, 2, 3, and 4. So it goes, the both curves intersect at 0, 0, and at 4, 2. Like that. So there's R right there. So I'll give that to you so you don't have to worry about graphing it. You can just have it there for yourselves. Okay? So that is the point, though, 4, 2. And, of course, 0, 0. So set up and evaluate that integral.
Can we evaluate it using our calculator?
It's a non-calculator problem, so you should be able to evaluate it without a calculator, too.
Oh, I can.
Okay, and I'll kind of come around and help as necessary here.
Oh, yeah.
Yeah. And it just gets
I'd recommend you rewrite square root of x as x to the 1/2, by the way. And x over 2 is 1/2 x.
When you multiply common bases, something that
You add exponents.
add x.
That was a fun one. Wow. What is that squares?
Volume, yes. Cross sections are squares.
Are square. There, okay. Integral seeking squared should give you tangent, you shouldn't really use a right, because look here, you like if you look at this, if you choose this here, which you can, you don't have the du here because you don't have a tangent of x.
Why?
So, but
You get some really goofy on me.
So that was just a tangent. So I think
Really? Really?
It gets worse. No, keep going. When you actually start getting answers, it's kind of goofy.
Are we doing over here questions or anything? So, I mean, that's a good start, and yes, that's the side squared. So what's your side? What determines your side? One of those.
We have the time.
You can imagine here that the cross section is going to come like here to here. So the square is going to come up, over, down. Up, over, down. So the side of that square is determined by the distance between those two curves, right? So
I don't know what that is.
Write that.
4 to the 3/2. I don't see how I would do this one exactly, because I don't know.
4 to the
Well-
3 has 4 cubed is 64, square root of 64.
Right.
But this is still goofy. Like, you still get some
Well, you don't have to
fractions.
evaluate. Remember, this is
Oh.
this is for response questions. So you're done once you've got your arithmetic there.
My answer right there.
But you're close though. You just need to flip it.
You have to write up the evaluation, right?
Sorry?
You have to write up the evaluation.
Right. You have to get it to the point where it's plugged in.
That was.
Question.
Simplified line, but yeah.
Sorry? So the region here, right? So that the square is going to be coming like from here to here. So what's that distance? The top curve minus the bottom curve.
Yeah, but how do you do it? Oh, okay. I was like, you can't just do y minus y.
Right. Okay, so here's, I'm going to show you your setup real quick because we're going to run out of time. There's your setup right there. Okay, there's your setup right there. Okay, and so then you have to FOIL that out, right? So I rewrote that as x to the 1/2 and 1/2 x, and I FOILed it out. So x to the 1/2 times x to the 1/2 is x to the 1, and then you multiply your inner terms together and your last terms together and stuff like that, and you simplify it down, you integrate, all that good stuff. Remember, once you integrate and you plug in those values, you're done, right? Once it's like plugged, once the values are plugged in, so I'm not quite done yet, I have one more little step there. We'll talk about it tomorrow. I recommend you guys look at your review packet that I just gave to you, okay, and try and find some of these volumes of known cross-sections problems to get some practice, maybe some solids revolution too. I'm not going to give you any homework other than that. So
that
start
it?
looking at those review packets. Yeah, start working on the review packets.
So that's the end of learning for
That's all calculus.
Guys, we've learned all calculus.
You finished